Guys, welcome back to chapter 13. For those of you taking my online class, this is the second half of chapter 13. So in the first half, we covered chemical equilibrium, we covered equilibrium constants. Now in the second half, we are going to cover 13.4 first. We're going to do some calculations, and then we'll finish off the chapter with Le Chatelier's principle. So up until this point, we have solved problems where we either knew all of the concentrations at equilibrium, or we knew everything in the equilibrium constant equation except for one thing. So maybe we knew the constant, we knew the initial, or we knew the concentrations of the reactant, we solved for the product, right? So far we've only had to really find one unknown. Now the problems are going to get a little bit more challenging. So the thing I like about these problems is they're a little bit more realistic, but reality is messy and they get a little bit harder. All right, so let's take a look at this type of example. So in this example, we want to determine the equilibrium concentrations when we know initial concentrations and one equilibrium concentration. So why is this a little bit more like reality? Well, before we do any chemical experiment, we typically know what it is that we're putting in. So I will know the initial concentrations of whatever I'm mixing together. I made it, I'm mixing it, I know initial concentrations. Knowing one equilibrium concentration. Now, that's kind of easy to do, right? If we have the right instrumentation, the right kind of experiment, we can reach in and determine what the concentration is once it's at equilibrium. Okay, so it's probably, it's not easy, but it can be done. And for those of you that are taking my class, this is exactly what we do in the lab, right? We measure the equilibrium concentration based on spectrometry. So how much light did it absorb or not absorb, okay? But at the end of the day, we need a new tool to help us solve these problems. They get a little bit more challenging. There's a lot more moving parts. So we need a tool or a skill to help us keep track of that. And the skill that we're going to use is something called an ICE table. ICE stands for, and I'll kind of set up what this table is going to look like. ICE stands for initial, change, equilibrium. So I for initial, C for change, E for equilibrium. So what we're going to do is we're going to use this acronym to help us track what was the initial concentration, how did that concentration happen or change during magical chemistry, and then what was that concentration at the end. The best way to get to know ICE tables is to dive in. Suppose we have a reaction in which the initial concentration of A is 1 molar and the initial concentration of B is 0. When equilibrium is reached, the concentration of A is now 0.75 molar. What is the equilibrium constant? So in this case, we're solving for K. There's a couple different ways you can start. I like to write the K value, so I like to kind of have that over to the side so I remember what my destination is. So remember K equals concentration of products over reactants. So we've got products, which is B, and that coefficient is going to become the exponent, over concentration of reactants, which is A. So eventually, I'm going to want the values to go in here. Now, this is a big thing to remember. The values that go into this equation are the concentrations at equilibrium, not initial. The values that go in here are concentrations at equilibrium. So now let's take a look at what an ICE table is going to look like. So an ice table is going to look like this. So across the top, we're going to put the concentration of our reactants and products. So here I'm going to put A, I'm going to put B. I also like to put the coefficient into the table just because it's going to be a good reminder. That's going to mean something. It's going to make a difference in the end. Okay. Then we put our acronym out to the side. So we make a line for initial, we make a line for change, and we make a line for equilibrium. Now we're going to start filling out the table. So let's read back through our problem. The initial concentration of A was 1 molar. So the initial concentration is going to go into the initial line. So that's a 1 for 1 molar. The initial concentration of B is 0 molar. So that's going to be 0 in the initial concentration. When equilibrium is reached, so at equilibrium, okay, that's what that means. When equilibrium is reached, the concentration of A is 0.75. So I would come down here and I would fill in what is the concentration of A at equilibrium. So I can come down here and fill in 0.75. That is all of the information that this table gives me. It doesn't give me any more information. But the good news is I have enough information to solve this problem. Okay? So if I know the initial and I know what the concentration was at equilibrium, I can determine the change for A. I can determine how much it changed. So to get from 1 molar to 0.75 molar, that was a change or a decrease of, so minus 0.25 molar. Okay, I'm going to do that in red. That way you know that it's the change. Red often indicates that we're losing. So minus 0.25. We actually now have enough information to fill the rest of the table with numbers as well. So let's think about what a chemical reaction is. We are taking whatever this molecule A is, and we are breaking it apart. We're decomposing it. And when it breaks apart, it's going to break apart into 2 molecules of B. So for every molecule of A that I have, it's going to break apart and it's going to become 2 molecules of B. So you're like, Ms. Maz, what does this like minus 0.25 change means? It means that we used up 0.25 moles of A to create B. We started with 1 mole, we used up 0.25 of those moles, and we still have 0.75 left over. Well, if I know how much A is going away, I also know how much B has been created. So the amount of A that goes away is the same amount of B that gets created, that 0.25. But what do we also have to consider? We also have to consider that for every A that broke apart, 2 of the B's formed. So if we used 0.25 moles of A, we made 0.25 moles of B, but each time we made 2 of them. So we have to multiply that by 2. So the change in this case is a positive 0.5. 2 times 0.25. All right, now that we know the change, we also can determine what the concentration of B was at equilibrium. So we've got 0 plus 0.5. So the equilibrium concentration of B is just 0.5. All right, so now our ice table is completely filled with numbers. That's a really good place to be. We're now going to take these values and we can plug them into our equation for K, okay? The only values that go into the K equation are the values down here at the bottom of our ice table. Nothing else is allowed to go into that equation. So let's do this. Let's determine the value for K. So I'm going to come over here to the left-hand side because I have room. So in this case, we've got K equals, so on the top is going to be the concentration of B at equilibrium, so that is the 0.5. And then don't forget to square that, right, because of that coefficient. And on the bottom is going to go the concentration of A at equilibrium, which is 0.75. So plug this into my calculator and chug through it. We've got 0.5 squared divided by 0.75, and the answer is 0.33. So K equals 0.33. So to summarize what we did here, we knew initial concentrations. We knew one of the equilibrium concentrations. We used an ice table to help us guide us through the problem to determine mathematically the equilibrium concentrations of A and B. And then once we were able to fill the entire chart in with numbers, determine the equilibrium concentrations of A and B, we then could plug that into our K equation to determine K. I've got lots more examples coming up in future videos, but this was your introduction to ice tables. I hope you found this helpful.